So let's look at rate in rotational systems, or rotational rate. So we have our learning goals there that we're going to look at. So we're going to be doing a little bit of angular velocity and angular acceleration and tying that into a linear velocity quantity. So your bell ringer for the day is this one. So what's needed to find the acceleration of an object? Alright, so this is just going back to our last lesson. Acceleration is going to be change in velocity over time. So we're going to need both a change in velocity and a time in order to figure out that acceleration. We could also say that this is equal to, so that change in velocity is final velocity minus initial velocity over time. So we would technically need three pieces. We need a final velocity, an initial velocity, and a time in order to find the acceleration of a scenario. So let's jump ahead to our content here. So we're going to be looking at rotational rate again. And starting out, we kind of have to remember we've done this a little bit before. So angular speed. So how does linear speed differ from angular speed? So angular speed is some kind of a circular motion. So we could be going clockwise like that, or we could be going counterclockwise like that. But remember, when we talked about this before, we're going through a degree measurement here, or radian measurement. So remember those, we have radians. Alright, so how we're getting those radians. So how does it differ from linear and angular speed? How do they differ? So linear speed is just the rate of motion in a straight line, and angular speed is the rate of motion through an angle. So remember, that would be theta, or that could also be a radian measurement. Okay, and if you forgot, 1 radian is equal to 57.3 degrees. So that is a conversion factor that we needed to remember from before. So let's kind of look at a scenario here. So we've talked about some theme park swings and stuff like this before. So this is spinning around in a circle, and we have the people on the swings there. And the scenarios we talked about this before were with centripetal acceleration or centripetal force, and then the centrifugal force, which is that non-existent force that makes things fly away. It's just a lack of tension or something like that. Okay, so we could, I know this is moving, but we could declare some point on this, and we could say that it's going around in this direction and back to the start, right? So that would be moving in a counterclockwise motion. So it's kind of going to the left to begin with. And depending on the time we're given, we have to figure out how many radians that's going through. All right? And then you'd have to find a point on there and count that. But this is an example of something where angular speed would be important, because they need to develop this motor to go fast enough to maintain that velocity or that angular speed, which pulls the riders out a little bit, make it a little bit more fun. If they made it so if they didn't know how to control angular speed in this system, then the people would just be sitting there and going really slow, close to the ground, and it'd be a really boring ride. So there's a lot of theme park rides that use angular speed and angular acceleration. Okay, so I keep talking about clockwise and counterclockwise. That's important in these scenarios. Okay, because that's how we determine positive and negative angular velocity in these scenarios, if it is going clockwise or counterclockwise. So what does a positive angular speed mean? That means that the object is going counterclockwise, and then negative would be going clockwise. Okay, if we remember back to our conversation, we've talked about a unit circle here. So this is going to be 0 degrees on a unit circle, and our angle measurements go up from the horizontal. So that would be a positive measure, which would be counterclockwise. Okay? And then if we go below the horizontal, that's going to be a negative measure, so clockwise would be negative. So we have to remember that counterclockwise positive, so that would be up from the horizontal, that's positive, and clockwise, which is down from the horizontal, that is negative. So how do we measure rotational speeds? So we use angular speed. We can go a little bit further and go with angular acceleration, which we'll be covering in a little bit. So we use this goofy looking W here, which is the Greek letter omega. Okay, so if you draw a W kind of curling inward like that, that's your omega, that's angular speed. So angular speed is measured in revolutions per minute, but most of the time we're going to be using radians per second unless it states otherwise. And the revolutions per minute, we've written it like this, and we've also done rotations per minute. Those are the same thing. So we just have to understand revolutions and rotations are going to be equal here. Now radians, if we convert from this to radians, we're going to have to do a little bit of work. So remember, one revolution, that would be going around the circle one time, is equal to 360 degrees or 2 pi radians. So we have to remember that conversion as well, which I'll write those down when we get to the problems here in a minute anyways. So our equation, angular speed is equal to angular displacement over time. So this is putting everything in words. So we have that angular displacement over time. And angular displacement is just a fancy way to say how many radians am I moving through, or what degree am I moving through. So we don't want degrees, we want radians. So more compact, this is our angular speed equation over here, or angular velocity, because we can speed and velocity here. If it's positive and negative, then we can do counterclockwise versus clockwise. That would be more of a velocity measurement. If we talk about speed, then sign does not matter. So omega, again, radians per second or revolutions per second. Up here we had revolutions per minute. When we're working with revolutions, it really depends on what the problem is asking for. I would say 9 times out of 10, I'm going to convert everything to radians per radians and seconds. So theta, so that's a Greek letter theta, is in radians, and that is time, which is seconds. So remember, theta is just the degree, so we're going to go from radians or degrees, we're going to have to switch them all into radians. So the next equation here is if we're given some kind of an angular speed or angular motion, we can convert that to a linear speed. So this is my linear velocity, that just means regular velocity, that's in meters per second. We're going to take the radius of whatever is spinning, or wherever we're measuring the radius from, times my angular velocity. Okay, so we have these over here. R is for radius, omega angular velocity, and V linear velocity, along with the correct units for each. So these would be the best units to use when I'm converting from linear speed to angular motion or angular speed, or vice versa. So let's look at an example problem here. So we have a weather radar antenna, and that is completing 160 revolutions in 1 hour. Find the angular speed in RPM, so that's rotations per minute, if it rotates clockwise. Okay, so let's think about what our final answer is going to be. So we are going clockwise, so that would be left or down from the horizontal. So we're going to have a negative velocity in the end, and we're going to have rotations per minute as our final answer, or revolutions per minute. So this, we're given 160 revolutions in 1 hour. So if we set up our equation, omega equals change in angle over time. And that change in angle, we know that's 160 revolutions. We can leave it in revolutions because that's what our final answer is asking for. So we have 160 revolutions or rotations. Since I wrote that before, I'll write rotations. And we have 160 of those in 1 hour. We need minutes. Okay, so this would be 160 rotations in 1 hour. That would be angular speed and rotations per hour, but we're going to have to convert that to minutes. So let's make some tracks here. And if I want to change from hours to minutes, then a little dimensional analysis. Hours goes up there, minutes goes down here. Hours will cancel out. And we would just be doing 160 divided by 60, which would get us 2.67 rotations per minute. Or we could just say RPM if we want to, make it a little bit nicer, RPM. And then remember we said that this was a negative, so that should be negative 2.67 RPMs because we're going clockwise. Okay, so let's check out another one down here. So a watch. This is a common example for angular motion and angular speed. So your watch rotates through 90 degrees in 15 seconds. what is the angular velocity of a watch? Alright, so we need our equation again. Omega equals change in angle over time. And our change in angle is 90 degrees, but we don't want to use 90 degrees, remember, because we need to use radians. So let's convert that to radians. So we're going to use quite a few tracks in this lesson here. We're going to convert from degrees to radians. So earlier I said, I'll write this up here, 1 radian is equal to 57.3 degrees. We need that, and 1 rotation or 1 revolution is equal to 2 pi radians. That's another, those two are some conversions that we're going to be using, or that you'll see me use throughout the lesson. So I would write those down somewhere, you're going to use them. So if I want to get rid of the degree symbol there, a little dimensional analysis tells me that I need to put my degrees down here on the bottom. So that 57.3 goes down on the bottom because I want that to cancel out. And that would be 1 radian. So that's going to take care of that. We'll do 90 over 57.3, and that's going to give us 1.57 in radians. So that can go for our change in degree. So 1.57 radians there over our time, which is 15 seconds. And then we can just put those two values in our calculator, and we will get 0.105 radians per second. And then again, we have to ask ourselves, is this going to be a positive or negative value? Well, my clock is going that way, so it's clockwise motion. I'm dropping below the horizontal, so that would mean that this is going to be a negative value. Okay, so always think about that horizontal is always off to the right. From there, where is my motion going to be? My clock is going that way, so that means my horizontal, or my motion, my angular motion is going down from the horizontal, which would be a negative value. So let's look at another one here. The computer's hard drive is spinning at 7,200 RPM, so that's rotations per minute, counterclockwise, so that means we're going to have a positive value in the end. What is the angular velocity in radians per second, and what is the velocity in meters per second of the hard drive at a radius of 0.0889 meters? So let's do the first part. So angular velocity is going to be, and we're actually just given that, really, so that's 7,200 RPM. And this is just kind of a conversion problem. So we have rotations per minute. We have to change that to radians per second. So this involves a little bit more conversion here. So let's set up some tracks to see if we can figure it out. So we have 7,200 rotations happening in 1 minute. And we want to change that to radians per second. Okay, so remember those conversion numbers I wrote on the last slide there. Let's take care of the easy one first. So we want to go from minutes to second. So minutes should be up here, seconds should be down here. That's going to get rid of those. So now we have it in seconds. And now we're going to take care of that rotation and turn it into radians. So I have 1 rotation, and remember that is 2 pi radians. So I don't want to leave everything in terms of pi. I'm going to put that as 3.14 in my calculator, or use it as a decimal, and see what we get. So when you put that all in your calculator, you get 753.98 radians per second. And that's positive because it's going counterclockwise. So comparatively, that looks like a big number compared to what we've seen before, but that's spinning 7,200 RPM, so that hard drive is moving pretty quick. So the second part, what is the velocity in meters per second of the hard drive at a radius of 0.0889? So if you forgot, we had an equation that we wrote down right here. So this relates linear velocity and angular velocity, which we're going to use for the second part here. So velocity equals that radius, so 0.0889 meters, times that angular velocity, which is 753.98 radians per second. And that's going to get us to meters per second. So when we multiply that out in our calculator, we get 67.03 meters per second. So on that hard drive, say we are, I don't know, 0.0889 meters, so that could be on the outside edge, that could be in here. That's more than likely on the outside, so it's about 8.9 centimeters out. So on the outside of that hard drive, we are rotating 67.03 meters per second, which is pretty quick. Alright, one more of these angular speed problems, and then we will look at angular acceleration. So the final one for angular velocity is a baseball player swinging a bat, and this one isn't too terrible. So we have that equation. We want to change this 270 degrees into radians just like we did before. So we need our degrees down here. That's 57.3 and 1 radian. So our degrees are going to cancel out, and we're going to get a radian measure. Which is 4.71. So 4.71 radians. We're going to put that in the numerator of our equation over here. 4.71 radians, and that's in 0.15 seconds. So put that in our calculator, and we get 31.41, so 31.41 radians per second. So that is the angular speed of the baseball player swinging the bat. And we mentioned counterclockwise here, so remember the direction is going to be positive. So we have a positive answer. So let's take a look now at some angular acceleration. So we're going to talk about the equation here. So essentially, angular acceleration, or acceleration in general, is how much am I speeding up? So what is my change in my speed or velocity over the time that I'm measuring? So how does angular acceleration differ from linear acceleration? It's just on an angle. All right, so we are rotating. How fast are we rotating? Linear acceleration is how fast are you increasing your linear speed. Okay, so this is your linear acceleration, and this would be our angular acceleration. How much is our angular acceleration? How much is our angular speed changing throughout that scenario? So we use the Greek letter alpha. Okay, it kind of looks like a fish, I guess, if you drew a fish and then the tail there, but alpha doesn't have the little tail there, so that's your alpha. And the angular acceleration equation is change in angular speed over time. And remember, that change in angular speed can be written as final minus initial speed. So if we write our regular acceleration equation here, it's change in velocity over time, which is final velocity minus initial velocity over time, and these are linear quantities. Okay, to relate this angular acceleration to linear acceleration, this is our equation for that. So acceleration equals radius times angular acceleration. So that could be another thing that you could write down. However, we can use our linear velocity equation, our linear and angular velocity equation, to get the same thing. So the units for the equation are in radians per second squared, because we are measuring an angle over time squared. So that's like meters per second over a second, or this would be radians per second over a second. So you could also see this sometimes, radians per second. That's the same thing as angular acceleration. Let's take a look at an angular acceleration scenario here. So how long will it take a basketball spinning on someone's finger to stop if it undergoes an angular acceleration of -15 or -0.15 radians per second squared? So we have -0.15 radians per second squared, and due to friction and drag, that's what causing that negative acceleration. That's actually a deceleration because it's slowing down, and it is initially traveling at 27 radians per second. So that is my initial angular velocity, that 27 radians per second. And there's some keywords here. It says how long does it take it to stop. So that means my final angular acceleration is going to be 0 radians per second. And now if we're looking at our variables that we have here, we need our equation, we can have that. So right here, so we need to do final minus initial over time. So I would have this equation handy when you're working on these types of problems, just so you can write everything out and plug everything in. So we have negative 0.15 radians per second squared for our angular acceleration. Final is 0 radians per second, and initial is 27 radians per second. And that is over a time of our unknown. We don't know that, so we're trying to find it. Okay, so 0 minus 27, that's just going to give us a negative 27 radians per second on top. And now we have to think about our algebra skills here. How are we going to solve this? Well, I never want to have a variable in the denominator, so I'm going to multiply both sides by time. So that will take care of that variable down there. And then we have time times the negative 0.15. So how would I get rid of the negative 0.15? We can write that a little bit nicer if we want to. Negative 0.15t equals negative 27. And we're going to divide both sides by negative 0.15. Throw that in our calculator, and we know that we're going to get a value for time, which will be 180 seconds. Okay. So if you have your signs right, and you're doing final minus initial, things will cancel out, and you'll get a positive value for time. Okay. Let's check out another one. So down here, so we have a person that they flip their bicycle over, starts the rear wheel spinning from rest. Okay, so that's a key word. To a final angular velocity of 275 rotations per minute in 5 seconds. Calculate the angular acceleration in radians per second squared. So I said RPMs here, rotations per minute, and we're looking to get radians per second squared. So we're going to have to do some conversion here to turn this into radians per second. And we're also using 5 seconds there. So that's how we know that we're going to have to change from minutes to seconds. And then this is how we know we're going to have to change from rotation to radians. So let's start by writing what we know. So we have a time of 5.00 seconds. We're going to start at rest. So our initial angular velocity would be 0 radians per second. And our final angular velocity that we have is 275 RPMs, which we're going to have to convert this. So we're going to do it right here. And we'll just write this as rotations on top and minutes on the bottom, just for the point, or for the purpose of using these tracks here. So, just like we did before, let's take care of minutes first. So 1 minute, 60 seconds, that's going to take care of those. And now we're going to go from rotations to radians. So 1 rotation, that is 2 pi radians. And we'll put this in our calculator to make it into radians per second. And we get 28.80 radians per second. And now we're going to use our acceleration equation to figure out what the acceleration is on this bicycle. So acceleration is going to be final, so 28.8 radians per second minus initial 0 radians per second over my time value, which is 5 seconds. So put that in your calculator, and we will get an acceleration of 5.76 radians per second squared. So for B, that was part A. For B, if we squeeze the brakes now, and we cause an angular acceleration of negative 87.3, so let's write that down, negative 87.3 radians per second squared. How long does it take the wheel to stop? Okay, so now for this one, we have to kind of think about what was happening before we squeezed the brakes. So before we squeezed the brakes, we sped it up, and we were getting an acceleration measurement, but what did we speed it up to? We were going 28.8 radians per second. And now for the second scenario, we're looking to get it to stop. So this is going to be my initial, because that's how fast it's going. And this is going to be my final, because we're looking to stop it. So we're going to have to do 0 minus that in our equation. So let's write down final angular velocity, 0 radians per second, and initial angular velocity is 28.8 radians per second. And let's go ahead and plug it into our equation. So negative 87.3 radians per second squared, that's our acceleration, equals change in angular velocity, which is going to be final, minus initial, over time. So that's what we're looking to find. We're looking to find how long it takes us to stop. So this problem is just kind of like the one we did above with the algebra. So we would multiply both sides by t to get rid of the t. I'm just going to save some time here. And then we divide both sides by negative 87.3. And that would give us our final value for time. We'd have a negative over a negative, which equals a positive. And we get a value for time of 0.33 seconds. So when we squeeze the brakes with causing that acceleration, it's going to take 0.33 seconds for that wheel to stop. Okay, so this one was a little bit more difficult. We had to kind of analyze the problem to figure out what was going on. But in general, we just needed to convert and then use our acceleration equation. Okay, that's how these work for the most part. So let's look at one more problem. So a motorcycle can accelerate from 0 to 30 meters per second, about 108 kilometers an hour, in 4.2 seconds. What is the angular acceleration of its 0.32 meter radius wheels? Okay, so the equation that I had you write down originally, since we are using 0 and 30 meters per second, we have to think about what kind of a value this is. This is just a regular velocity or linear velocity. Okay, it's a linear velocity, so that means we're probably going to be using this equation, which was our related linear velocity with angular velocity, because we're also using a radius. Okay, we could also use our linear acceleration equation, but this is the one that I explicitly told you guys to write down, so let's use this problem. So let's write down, or let's pull this off to the side here. We have our angular acceleration equation there. So just so if we need it, we shouldn't need it to this point in time, but we're going to have to do a final minus initial over a time. Well, we're going to have to convert these to radians per second by using our linear velocity equation. So this one, 0, pretty easy. You just plug it in there, you're going to get a 0. So my initial angular velocity is 0 radians per second. And the final, it's going to take a little bit more work, but we have 30 meters per second, and then we have that radius. Remember, that's what that is, so that 0.32 goes in there. So 0.32 meters times angular velocity. We can call that final if we want to. So we'll have to divide both sides by 0.32 to get rid of my meters here, and we get a final angular velocity of 93.75 radians per second. So now we're going to use this with this and our time value to find our angular acceleration. So alpha equals final, 93.75, minus initial, which is 0, over time, which is 4.2 seconds. Plug that in our calculator, and we get 22.32 radians per second squared. So we took the linear velocity of the wheels here, okay, the wheels pushing on the ground going that way. We took the linear velocity of the wheels and we converted that first to angular velocity by using our equation here that relates the two, and then we plugged those angular velocities into our acceleration equation to find the angular acceleration of the wheels to be 22.32 radians per second squared. Okay, so that concludes our lesson on linear and angular velocities. I would suggest practicing these. If you have more questions on these, let me know. Send me an email or comment below. I appreciate you watching. Thank you.